I see thumbs up at the back. Okay. So I'm going to talk about something that I don't really know much about. Star clusters are interesting, but mainly I work on galactic structure, so wherever possible, this series will focus on galactic structure from my point of view. Here's how I see the lecture series. I haven't discussed this with either of my, well, I discussed it vaguely, I guess, with Kathy, but I see this as a lecture series in 3 parts. There's how do stars form. Kathy's going to talk about that, talking about small scales. How do clusters form and evolve, and that's Bob's prerequisite, 10 to 100 parsec scales. Everything bigger than that is mine. So how does the field evolve? How does star formation within clusters tie into the field? And this is kind of what I figured out for myself as my motivation for this lecture series, which is how do star clusters trace the evolution of stellar populations over galactic history, and what role did they play in galactic evolution? I won't necessarily tie everything I say into that, but that I think is kind of the underlying theme from my perspective. It's how do you build galaxies? Why do you want to understand that? Well, galaxy formation, I think, is still one of the fundamental problems in astronomy. Understanding how stars form is clearly crucial to understanding how galaxies form. And the Milky Way can tell us a lot about this bigger question. You know, where are stars forming now in the Milky Way? What's the history of star formation in the Milky Way? What's the formation history of the galactic disk, to focus in one part in particular, which is where most of the star clusters are nowadays? How typical is the Milky Way among galaxies? And actually, let me, one thing I was going to do, let me put out a timer for myself so that I know this talk is too long. It will tell me where to stop in the talk. How typical is the Milky Way? What drives the differences between galaxies? What's the origin of the Hubble sequence? Now, these are all big questions, and I'm not going to answer any of them. But these are questions that you should be thinking of, and there may be some things in here that might be of some use to you later on. Probably not what I say, but what Bob and Kathy will say. The third introductory slide for me, this is how I've laid out the talks that I'm giving. The first one is mainly talking about the galactic demographics, what the galaxy is like now. It's a lot of basic stuff, some of which I thought I knew, but I didn't. So I find it useful just going through this. And at the end of it, if there's time, I'll go into a bit about techniques that I think is a kind of basic set of a toolbox for some things that you might think you know, and you probably do know, but I didn't. The solar neighborhood is the subject of the next lecture. Talking there about the nearby stars and the initial mass function. I've tried not to talk too much about the initial mass function because that's what I really like, but there's something in there about it. Third lecture is about dynamical evolution, radial migration, something I didn't know much about, and I still don't know that much about, but it's a very interesting topic. Fourth lecture is actually moving a little bit off target. I'm going to talk about the halo. Partly the reason why I'm talking about the halo is because this year there's a significant anniversary that not many other people seem to be celebrating, so I'm going to celebrate it here. And there are globular clusters, which are star clusters, which is what this is about. And actually, and everything we thought we knew about globular clusters turns out to be wrong. So they're actually much more interesting now than they were 5 or 6 years ago. Fifth lecture about the star formation history in the disk. This one still has to be finished written, so I'm not quite sure what it's going to say, but the age metallicity distribution is going to be something that I'll talk about there. Sixth lecture, where did the field come from? Whence the field is the way that Michael expressed it. And then the final lecture, I'll talk a bit about the sun and what kind of constraints we have and where it was born. Overall, it's going to be observational approach. Egan once said he says, whenever a theoretician talks about doing observations, the theoretician talks about getting their hands dirty. Whenever I think about doing theory, I think about sitting back in my chair and getting my mind dirty. So, and I will try and highlight throughout this some of the upcoming missions, particularly Gaia and the James Webb Space Telescope. But there are also large-scale surveys that are going on the ground. VISTA, PanSTARRS, LSST will be starting up sometime. And then you've got EALT, which may be the only, well, I'll not go there. Okay, EALT and maybe GSMT. Okay, this talk. Last introductory talk before we actually get talking about it. We're going to talk about the large-scale properties of the Milky Way. a bit about the disk, a bit about the sun's location, some basic stuff about spiral structure, a little bit background, clusters and associations, the basic terminology there, the star formation rate in the Milky Way, some chemical composition and abundance gradients in the disk. And now let's actually start talking. So the Milky Way is a spiral galaxy. This is the Derby image of the plane, the plane of the Milky Way, peanut bulge in the center. And of course we now know, and this is probably the only joke, there is in fact a bar at the center of the Milky Way. The constituent populations, we're all familiar with this. There's the galactic halo, a large spherical structure which is generally characterized by globular clusters. The disk itself, which is where the sun lives, perhaps 10 kiloparsecs in radius. The central bulge, which we still don't really understand how the bulge formed. It now looks as if the bulge is mainly dominated by a bar-like structure in there. The disk itself is rotating. It's usually subdivided into two components, the thin disk and the thick disk. We'll say a bit more about that later. I think that actually turns out to be, it's both a simplification and an overcomplication. Probably there's just one disk there. I think there's some recent evidence that actually gives a very good explanation of how the thick disk, why we see a thick disk. The stars are there, but their origin is perhaps not as complicated as we might have thought. Okay. The gross properties. So these are from Sidney Vandenberg, the paper by Macmillan, Freeman and Bland Hawthorne, but just to give you a scale for our galaxy. The total virial mass looks like it's about 10 to the 12 solar masses. Going out to 60 kiloparsecs, you're talking about 6 times 10 to the 11 solar masses. And actually, that 5% is in the wrong place. That should be down here. The stellar mass within the galaxy is only about 5%. So 95% of the mass contributing within the Milky Way is dark matter. Within that stellar component, you have a central bulge. There's the halo, and then the disk. And interesting, these numbers don't add up, do they? Do they? Yes, they do, I guess. So most of the mass looks like it's within the disk of the Milky Way. And the halo is probably the lowest mass component of the lot. The total luminosity, estimated for the Milky Way, is about 2 times 10 to the 10 L sun, which is about 1/10 of an L star. L star is the luminosity of a galaxy that's on the knee of the Schechter luminosity function. I had never tried to tie in the Milky Way in this scale before, and actually I think this is right in terms of where L star is, but it's actually difficult to tie down that number. But the absolute magnitude for the Milky Way is about MV of minus 21. So it's a fair-sized spiral galaxy. It's not immense, but it's a substantial beast. Analogues for the Milky Way. This was an interesting exercise. The Milky Way is generally described as an SPC spiral. When you go into the literature and try and find galaxies that are described as analogues, none of them appear to be SPCs. NGC 6744 is described as an analog of the Milky Way. It's twice the diameter, it's not as bright as the Milky Way. And it's an SAB galaxy. NGC 7331 is another one that's been described as an analog of the Milky Way. It's not as luminous. I guess we're losing the bottom there, but never mind. It's not quite as luminous as the Milky Way. It's described as an SAB spiral. But this is the big picture of what our galaxy looks like. So coming down to looking at the structure of the galaxy itself. The classic work on the density structure of disk galaxies goes back to Ken Freeman's analysis of surface photometry of galaxies back in 1970. Basically taking photographic plates, scanning them in digitizing machines, and measuring the density profile. And what Ken Freeman came up with was that the density distribution within, and I guess I should be using the mouse for this, but I'm pointing by hand. The density distribution within a galactic disk was well represented by an exponential. So this is M83, a type 2 spiral galaxy. It's I guess an SC. And then NGC 449, which is more like what we think the Milky Way is. So you have the central component, which is the bulge, and then the disk outside that fits an exponential distribution, just characterized by a scale length. So this was the Freeman law for disk galaxies. Piet van der Kruijt and Leonard Searle took that a step further in the early 80s with scans of, I think, a total of something like 9 edge-on disk galaxies, and provided detailed density profiles. They not only looked at the scale length, they also looked at the scale height, so taking cross cuts across the galactic disk. They took, you can't read that from where you are, but I mean, you'll be able to see it's a sec-squared distribution, which is essentially a sec-squared is equivalent to an exponential in the density distribution. But the sec-squared you can tie back to dynamics. I forget who, in the early 1950s, if you take an isothermal sheet, you'll come up with a sec-squared distribution, which matches an exponential further out. The interesting thing that Van der Kruijt and Searle discovered was that you don't just have a single exponential as you cut up there. Basically, the density law deviates from a simple exponential as you get to heights of about a kiloparsec above the plane. This is what became known as the galactic thick disk. So in NGC 4565, they found a thick disk component. David Burstein had looked at S0 galaxies earlier and come up with the same result, that a simple exponential was not sufficient to explain the vertical density profile. The other interesting thing that Van der Kruijt and Searle pulled out was the fact that the disk, in all of the galaxies that they looked at, there was a truncation point in the disk in radial terms. When you got at the radial density law that Ken Freeman had pointed out, the exponential law fitted pretty well, going out over several scale lengths, and then there was a sharp drop at some particular distance where the density law fell sharply below the predictions of the scale of the extrapolating the exponential. So within these galaxies, Van der Kruijt and Searle found scale lengths in the disk of 2.5 to 5.5 kiloparsecs, vertical scale heights between 600 parsecs and 1700 parsecs. So this is actually from the sec-squared, the equivalent exponential scale height you divide by 2, so it's a 300 parsec to an 850 parsec scale height. And then the disks in all of these galaxies truncated at 3.5 to 5.5 scale lengths, which is saying that at some point star formation changes. So there is actually, more recent observations have shown that star formation doesn't stop at the edge of the disk, it goes beyond there. There's been work done by, particularly with Galactic, ultraviolet satellite, imaging some nearby spirals. This is M83. If you took the Van der Kruijt and Searle profile, the cutoff is where you can, basically they're at kind of the sharp edge of the light profile. This is the UV image. This has some H1 data superimposed in it as the red that you may very well not be able to see at the back there. There is some evidence for star formation going on beyond the edge of the disk. It's at a much lower level than you would expect just by extrapolating the Freeman law. But there is something going on out here. And that's something we'll come back to later on when it comes to talking about the initial mass function and possible changes in it. So, but this is, and again, this is just putting this is actually putting Galactic data together with H alpha data for M83, showing the active star forming regions within that galaxy. So, coming back to the Milky Way itself, some basic questions. Where's the sun? We actually know that pretty well in terms of where the sun is in relation to the midplane of the galactic disks. It's a very simple thing to calculate, it turns out. There's two ways of doing it. One is you just count stars. You take the stellar density law looking towards the north galactic pole and then the south galactic pole, and they don't match. And the reason that they don't match is because you're sitting above the disk. You're actually closer to the north galactic pole than the south galactic pole, if you like. Matching the two, you find that the offset between the midplane of the disk and where the sun is about 15 to 20 parsecs. You can do the same exercise by looking at young objects within the plane. Again, you're making the assumption that things are fairly symmetrical. So when you look at things that are young, that are fairly confined to the plane, things like young star clusters, Cepheids, OB stars, they'll be evenly distributed north and south of the midplane. I mean, maybe this is a theoretical concept, but it does actually seem to work, that looking at Cepheids, looking at OB stars, looking at young clusters, you get a consistent answer that the sun is something like 20 parsecs above the midplane of the galactic disk. How far is the sun from the center of the galaxy? It's about 8.5 kiloparsecs. How do we know that? One way has been looking at objects within the galactic bulge, RR Lyraes, distance indicators there, looking at their density distribution and working out where the peak is. This is an area where Gaia is going to play a big part, not necessarily directly measuring the distance to the galactic center, but tying down the luminosities of these distance indicators with much higher precision. Given a distance indicator, you look at the density law, and with both the RR Lyraes and type 2 Cepheids, which are both population 2 systems, you get a distance of something like 8 kiloparsecs to the centroid of the Milky Way. The other way is to look at Sagittarius A star, or objects very close to the galactic center, which are detectable at radio wavelengths, and you can do extremely precise measurements at radio wavelengths, very precise astrometry using VLBI. So you can actually measure the proper motion of the sun relative, well, you're measuring the proper motion of Sagittarius A star, but that proper motion is due to the reflex motion of the sun as it's in orbit around the galaxy. You can estimate the sun's orbital velocity using the galactic rotation curve, which you can measure from H2, from H1 measurements. That gives you a distance then about 8.4 kiloparsecs into the galactic center. The other way that you can measure the distance is to look at OH masers in star-forming regions. They aren't actually located within the galactic center, but measuring their velocity and tying. OH masers are associated with very young objects within the galactic plane, usually associated with star-forming regions. If you have a rotation curve for the galaxy, you can tie in their measured velocity to that rotation curve, and again measure the distance to the galactic center. And that's all. It's off the bottom here, but it comes out at about 8.2 kiloparsecs. So we know the distance to the galactic center to about 5%. We know our position relative to the midplane of the disk to actually somewhat higher precision.
How thick is the disk, the distance where the sun is?
Well, the scale light typically associated with that might be the next one. Scale light is typically given as something like 300 parsecs. But in its thickness, I don't know that we know the density profile particularly well within this very central region. And tracing that is actually quite difficult. So this is the local version of what van der Cruyt and Searle did. This is something that I did a long time ago, working with Jerry Gilmore. Simple star counts towards the South Galactic Pole. You measure, this was all done from photographic plates. Nowadays, you can do this simply with, well, you can see you do this from things like Sloan, you do this from pan-stars. Here we scanned the photographic plates, got the colors, used the colors to estimate the absolute magnitude of the stars, worked out the density distribution as a function of height above the plane, and we found the same thing in our galaxy that van der Cruyt and Searle found in these external galaxies, that a simple exponential, which is what had been assumed, did not fit the data. Once you got above a kiloparsec, the number densities, so this is density and this is distance above the plane. Once you get above a kiloparsec or so, the densities are higher than predicted based on a simple exponential. We took the simple thing. If all astronomers, if you give them data, all observational astronomers, if you give them data, will first of all try to fit a straight line. If that does not work, you fit two straight lines. If that works pretty well, you stop. So that's what we did. And we fitted the second component here, which is it's a reasonable fit to the data. Scale height is about 1.5 kiloparsecs instead of the 300 parsecs. This is what we call the galactic thick disk. You can extrapolate back locally and estimate. If you take these two combinations of density laws for the thin disk and the thick disk, you'd estimate about 2% of the stars locally belong to the thick disk. Now, since then, there have been multiple measurements, most recently involving things like the Sloan Digital Sky Survey, where you have much more accurate photometry, but still basically using the same techniques. You can fit, if you fit, this is obvious, but if you fit out here with a shallower power law, shallower exponential, you're going to extrapolate to higher local density. And there's been a lot of to and fro in the literature about what the local density of thick-disk stars really might be. And I'll get on to talking about that later, but there's no question that there is this excess here. The galaxy is not a simple exponential disk. How you explain it is something that's been taken a long time to come up with an answer in the literature, and I think we understand that now. But this is one area, this is an example of where one should draw a clear distinction between how you are representing the data and what the data are actually telling you, what the physics underlying the data is. Just because you fit two exponential distributions doesn't mean that that has anything to do with the physics. You shouldn't get tied up with thinking that how you fit the data really tells you what is going on. It's a simple way of representing what's going on here. This is something that you can take generally and apply to almost anywhere in astronomy. Look at what the data are saying, try and represent it in some way, but don't believe that your representation is necessarily the only way of doing it or necessarily telling you anything about physics. It's a mathematical model, that's all. Okay, so this is the following up here. Here are some of the numbers that people have come up with. Typically, you get scale heights of about 300 parsecs for the disk. The scale length measured, this is radially within the galaxy, for the thin disk is typically 2.5 to 3 kiloparsecs, except for Peter van der Kruijt did an excellent experiment where he actually took Pioneer 10 observations of Pioneer 10, I think it went to the outer solar system. It also obtained a map of the flux density of the sky. And he measured took that measurement and tried to estimate a scale length for the galactic disk. He came up with 4.5 kiloparsecs. Everything else comes in lower. And then for the thick disk, the scale heights that people are talking about are between 600 parsecs and a kiloparsec. The higher the scale height, the lower the local density. But typically people nowadays are talking about a kiloparsec and about 10% of the stars locally being in the thick disk. And this does actually tie through in other ways, although it's, as I say, it's not the correct answer, but the numbers are about right. And then in terms of the edge of the disk, using star counts, you can show that around about 14 kiloparsecs from the galactic center, so about 6 kiloparsecs beyond us in the disk, there appears to be a sharp drop. So our galaxy shares this characteristic with other galaxies, that there's an edge in the disk. That there's some star formation going on beyond there, but there's some kind of threshold that stops the same kind of star formation going on as within the inner part. Spiral arms. This is mainly an excuse to show pretty pictures, but spiral arms are where star clusters are forming. The spiral arm represents some kind of response to a density wave from the galactic center. The density wave is collecting up gas, compressing it, forming stars, and you have this beautiful, this is some observations that Rich Rand did back in the 1990s of M51, which I think is the poster child for how star formation works in spiral arms. That you can clearly distinguish where the gas is, where the dust is in here, the red stuff here is H alpha emission, the blue light are young star clusters forming, and you can see the sequence of gas to star formation, to obscure star formation, to clusters appearing as the density wave moves through the galaxy. So the gas is offset from where the stars are actually forming. Okay. For the Milky Way itself, there are 4 spiral arms that have been identified, and then there's this feature known as the Orion spur. Again, we have the central bar within the galaxy. This region of the galaxy here is obscured by the galactic center and lots of dust. But most of the young clusters lie along these spiral arms here. In fact, that's why spiral arms were discovered, because in the early 1950s, Morgan went and looked at where the OB stars were and mapped them out on a giant map of the galaxy and found that they lined up. So star-forming regions. So this is just a kind of basic prescription into the different kinds of star clusters that I think we're going to be talking about. And Bob can correct me if I'm wrong. But there are OB associations, which are large, gravitationally unbound regions where star formation is going on. They're typically, they can be up to a few hundred parsecs in size. They're typically, as it says OB association, obviously that's where they're characterized by the presence of O to B2 stars. It's a very relatively low star density. That's not much different than the star density within the solar neighborhood. Typical age is less than about 15 million years, and there's a dozen of them within 650 parsecs. Open clusters that we know and love. Here's, I think this is M36. Typical sizes of a few parsecs, 100 to 1,000 solar masses, densities of a few stars per cubic parsec, and obviously that changes based on where you are within the open cluster. They are gravitationally bound systems, and most of them are younger than about 250 million years. Embedded clusters, and these are something I'll talk about later on. These are the precursors to some open clusters. They can be much smaller in number than the open clusters, and there's a reason for that, as we'll come and talk about. Size is 100 to 1,000 solar masses, typical, the same as to the open clusters. They're gravitationally bound, at least where they are at the moment. But one important qualification to put in there is that part of the binding energy rests with the gas. These are clusters that are forming. They're younger than 10 million years. They're embedded within molecular clouds. Part of the binding energy sits with the gas. And what will happen, of course, is that if you form massive stars and you disperse the gas, they can become gravitationally unbound. And then finally, since I wanted to talk about the halo, globular clusters. They're a different beast from anything that we can see in the open cluster regime. They are more massive. They have a much higher star density. They're substantially older, obviously. These are 10 to 13 billion years old. These are the first massive objects that formed within the galaxy. And I think we're now starting to recognize that they played a much stronger role than we previously thought in building the galactic halo. So, just to give you the overview in terms of how these different clusters fit together. Globular clusters are all old. This is age and metal abundance. Solar abundance is here. Here are the open clusters. The Hyades cluster is slightly more metal rich than the Sun. M67 round about the Sun's age, round about the Sun's metallicity. And a few open clusters, mainly objects that sit at actually fairly high latitude, that come through the disk very rarely, that are almost 10 billion years old and comparable in age to probably the youngest globular clusters. And this is just the same plot, but this time with error bars to show that somebody actually measured something. And you will see that measuring ages is something that we're not good at. It's something where even Gaia probably won't help. But getting ages for these objects, getting ages in general, is something that's actually pretty tricky. Okay, so what's the star formation rate within the galaxy? This is something that I hadn't actually thought about much until this lecture series, so I don't know whether you've thought about it much at all. One thing again, like most properties of the Milky Way, it's much easier to measure this quantity in other galaxies than it is within our own system. When you're sitting within a galaxy, it's actually quite difficult to measure global parameters, which is what you're trying to measure here. There's a lot of different ways of measuring the total star formation rate within a galaxy, within a system. Almost all of them tie into massive objects. You can measure the X-ray flux, which is looking at the most massive stars. You can measure the UV flux, which is looking at high mass and intermediate mass stars. H-alpha, which is telling you the ionizing flux from, again, the most massive stars. You can look at dust and PAH emission, which is re-radiated emission from the most massive stars. There's a theme coming in. Dust, again, it's re-radiating emission, mainly from the brightest stars around. You can count stars, and that's easiest for the most luminous or most massive stars. And then you can look at free emission from ionizing photons, which come from, wait for it, the massive stars. So everything you measure here about star formation rate is tied into the massive stars. So if you want to know the total star formation rate in the galaxy, you need to take that number for the massive stars and put in your favorite thing for the mass function. And almost every star that you're forming is actually much less massive than what you're measuring. So that's a big caveat that goes into all of these measurements. But you have to assume some form for the IMF to tie what you're measuring into the global parameter. But you can do that. And this is a nice slide I stole from Daniela Calzetti, which shows the electromagnetic spectrum and all the different, where you can measure these properties. Out here in the infrared, you're measuring dust. Here, you're measuring direct starlight. So if you do that, you can come up with a formula. This is a paper by Calzetti et al., which takes each of these flux measurements and gives you a formula for converting it into a total star formation rate, m suns per year. All the way, actually radio, that's free emission and so on down there. So all of these can be calibrated, and it's very easy to measure these properties for galaxies like this. This is the SINGS galaxy sample. You do that, and here's the relation that you come up with for external galaxies. Absolute blue magnitude going from -10 to -20, and then star formation rate and solar masses per year, logarithmic 10 to the -6, 1 solar mass per year. This is the absolute blue magnitude of the Milky Way, so you would hope it was somewhere in here that you'd measure. And surprisingly enough, when you look at the measurements, when you look at the Milky Way itself, there's a nice paper by Komijok and Povic that pulls together a lot of different estimates of the star formation rate within the Milky Way. Looking at radio, looking at COBE, far infrared, looking at OB star counts, looking at gamma ray emission, far infrared continuum, WMAP measurements, and then Spitzer infrared measurements. You pull all that stuff together, and remarkably, you get a consistent answer from all these. Basically, the star formation rate from all these indicators for the Milky Way as a whole is roughly 1 to 2 solar masses per year, or 1 to 2.5. The average is actually 1.9 plus or minus 0.4 solar masses going into stars per year. And when you plug that into the relation that I showed, the Milky Way does actually sit round about where it should do. So it's a normal galaxy in terms of the star formation rate. And the star formation rate is a few solar masses per year, or 1 to 2 solar masses per year. Okay, next fundamental thing that one needs to measure is abundances. When you measure the abundance of a star, you're always measuring its abundance relative to the sun. It's a relative measurement. There are two ways of doing that. Photometric indicators, where you're taking a broadband flux and tying it in through a calibration and some standards to basically you're measuring differential blanketing from different features. And Stromgren is one way of doing that. DDO photometry. UBV excess is something else that I'll be talking about in the halo. This is something you can do easily for lots of stars. It's also something that's liable to be subject to systematic errors. We'll talk a bit about that later. A better way of getting abundances is from spectroscopic analysis, where you do things line by line. Curve of growth measurements was the old-fashioned way. Spectral synthesis is how you do it nowadays. This is expensive in terms of observation time. This is not. This gives you precise answers. This sometimes doesn't. When you turn to gas measurements, then you're switching to a different regime. Gas, you measure emission lines, you measure absolute abundances. And that's important. There's a real difference there. Gas measurements, as we'll see, are the way that people go when they're trying to measure radial abundance gradients in galaxies, because you're looking at H2 regions most of the time. The other thing about gas measurements is that if you're going to tie them into the sun's abundance, you need to know the absolute measurement of abundances of elements in the sun. And that, it turns out, is tricky. This is, within the solar system, we have a big advantage that we don't just have to look at the sun itself and try and interpret its spectrum. We can actually get chunks of material from the early solar system and do measurements in the laboratory on them to figure out abundances. So this is from measurements of meteoritic material, and you can see, you can also measure Earth, I suppose. We're standing on bits of what used to be the solar system. Well, I guess it still is the solar system. So you can measure very accurate abundances all the way out in this periodic series here. This is meteoritic material. The scale here is logarithmic, with the formal hydrogen abundance in the sun set at 12. These are actual measurements for the sun itself from the review article by Asplund et al. You see, this is hydrogen, this is helium. The next most abundant element is oxygen. And that's interesting because we just don't quite understand what the abundance of oxygen. This is from measurements made by Asplund and collaborators. Back in the 1998, Graves and Sauval came up with a really high precision measurement for the sun. Hydrogen is 12. For the oxygen, they got 8.83. 7 years later, Asplund and collaborators reduced that abundance by about 2/3. That's pretty major, because you're taking the third most abundant element in the sun and you're cutting its abundance by a factor of 2/3. That affects a lot of things about the sun. Oxygen is a really strong contributor of opacity within the internal part, within the sun, because it's such an abundant element. It dominates the heavy element abundance in the sun. There have been a couple of remeasurements since then, and the direct measurements of the solar oxygen abundance are sticking down there at this low level. And that's a problem for helioseismology. Helioseismology is where you're measuring the pulsations of the sun. You can match those, basically the pulsations depend on the opacity in the inner part of the sun, and that opacity is dominated by oxygen. You can match what you see very well with the high oxygen abundance. You don't do a good job with the low oxygen abundance. It changes the mean molecular weight within the sun. And that conflict is a problem. The other reason why it's a problem, or why it's interesting, actually I didn't put it up here. This also comes in when you talk about where the sun was born. Because one of the things that we'll talk about later on is looking at the sun's oxygen abundance relative to the ISM. If you take this high number, then the sun appears more metal-rich than the local ISM. If you take this number, it's perfectly consistent with the local ISM. One of the reasons why people started talking about radial migration for the sun, bringing the sun into where it is now from the inner galaxy, was because of this oxygen abundance. If that's gone away, do we still need to migrate the sun? In some ways it doesn't matter, because migration seems to be happening anyway, but still it's interesting. Other basic side of metal abundance is that basically as the galaxy has aged, it's got more metal rich. This is metal abundance, iron abundance. This is calcium to Fe ratio. So globular clusters are down here in the metal poor part of the diagram. Then the disk and the open clusters up in the metal rich part of the diagram. As you get to more metal poor stars, calcium is significantly more abundant than one would expect. It's more abundant than solar. The reason why this is that calcium is one of the alpha elements. Alpha elements are produced within type 2 supernovae. They're produced by alpha capture. What we believe happens, and this goes back to a seminal paper by Mattiucci and Greggio back in 1985. This is when the galaxy was young. All supernova that were polluting the ISM were type 2 supernovae. They were massive stars going pop and spewing their products into the ISM. Once you get to an age of about 1 billion years, type 1 supernovae enter the picture. Type 1 supernovae, as far as we know, this still seems to be the best picture, are a white dwarf that accretes material from a companion star, and the white dwarf goes over the Chandrasekhar mass and goes supernova. Those supernovae produce more iron. So as you add type 1 supernovae into the mix, you start to bring down this calcium to iron ratio as you bring up the iron abundance. What this observationally, what this says is that there's a signature for things that formed rapidly, as opposed to things that formed later on in the galaxy. And that's something we'll come back to later on as well. Okay. 10 minutes? 15? Excellent. So where is the sun in relation to all of this abundant stuff? Well, the sun actually looks like it's pretty average for the local stars. This is different. About 5 years ago, the standard picture was that the sun was more metal rich. That had nothing to do with the oxygen abundance. That was a separate thing. If you looked at the distribution, so this is a plot of the number, this is metallicity, minus a half, 0 plus a half, and number of objects from a couple of samples, one survey that I did, and then one survey that Misha Haywood did. This is solar abundance, and it's near the mode of the distribution. About 5 years ago, this whole thing was shifted to the left, basically because of an error in the Stromgren photometry. But it looks like the sun is about average for where we are now. There's about 40% of stars are more metal rich, 5% of stars are metal poor down here. If you look at the Milky Way as a whole, external galaxies all have abundance gradients. So this is distance from the center and metallicity for a whole bunch of spiral galaxies. They all show a trend with more metals in the center, which is kind of what you'd expect, that things fall in towards the center. There's more star formation in the center. You build up higher metallicity in the center. And when you look at the Milky Way, that's actually what you find too. Here, this is H2 regions. So this is oxygen abundance. This is oxygen, silicon, and magnesium abundance. There's a trend of about 0.1 dex per kiloparsec, that things are more metal rich in the center than they are on the outside. This is the plot here this is the old abundance of oxygen for the sun, where it's offset from the mean locally. But you'll see there's also quite a bit of scatter. We'll come to talk about that again later as well. And actually it looks like as you go beyond maybe 10 kiloparsecs or so, maybe this simple linear gradient flattens out a bit more. So again, a simple straight line is probably not the best representation. So this is kind of it. So these are a few pieces for what the Milky Way looks like that I'll be returning to later on in the lecture series. That I hope this has been a kind of introduction. So, but before going on any further, let's talk about some of the techniques. Any thinking Basset knows that when you're doing observational astronomy, you need to be careful in what methods you use. This slide is important just for one thing. Something that has always irritated me is people who confuse equinox and epoch. Equinox is where the first point of Aries is. It's the reference system. Epoch is when you do the observations. I just mentioned that. So, sample bind. Whenever you're measuring something from a group of objects, there are two things you need to worry about: individual errors and statistical corrections. Individual errors apply to individual objects. They can result from systematic errors in calibration, and you have to apply them when those errors exist. You apply them to the object one by one. There's also another type of correction that is statistical. Malmquist bias, Lutz-Kelker bias are the two obvious examples. Those are biases that only get applied. You never apply these corrections on a star-by-star basis. These corrections you apply to the sample as a whole, and the corrections can change depending on how you define your sample. One star may appear in 3 different samples and have 3 different corrections. So Mike thought it would be a good idea to go over this, so we'll just do this. So systematics. This is a color magnitude diagram based on stars with accurate parallax. Most of these, actually down to here, almost all of these objects are from Hipparchus. Down below here, it's all ground-based observations. Absolute magnitude, V minus I color. And this kink relation here is just an observational representation. These are metal-poor stars. These are subdwarfs. Very, very metal-poor and intermediate metal-poor objects lying below the main sequence. This dashed line here is a theoretical set of tracks which shows that nobody actually can actually model M-dwarfs yet. The important thing about this diagram is this kink in here. This is completely banal, but if you were to fit, let me go back. If you were to fit a nice smooth relation to this distribution, what will happen is that it does not go through these, it does not fit this kink in the diagram here. If you take a smooth curve through here, and I'm saying this because I did it, if you take a smooth curve through here, and you try and use the photometric parallax technique, take the color, go to the absolute magnitude, and then estimate the density, you get systematic mistakes. You will estimate that if you take a smooth curve through here, you're going to say these objects are fainter than they are, so you make them closer. So you increase the density. These ones you put too far away, and you'll underestimate the density. This is how you can take a smooth distribution and put a spurious peak into it. So a general point, but when you have a data set, initially a smooth curve might be the way to go, but as you collect more and more data with more and more accuracy, you should really go back and take a close look at what's going on there. I should say that we don't actually understand, I don't think we understand what's going on here. This is round about M3 on the main sequence. It's about where you switch from having a radiative core to being fully convective. If you interpret this in simplistic terms, what's happening here is that there's a sharp change in the radius of the star at this point. That things are over this very small range in temperature. You've got a large range in luminosity. So the only thing that's left to change is the radius. But you know, we still don't quite understand what's going on there. But so this is just a flag that says beware of smooth curves that don't quite fit the data. Malmquist bias. There's Mr. Malmquist. Consider a set of stars of a given spectral type with a given absolute magnitude, and there's a dispersion in that absolute magnitude of sigma. Assume that that dispersion is Gaussian, and it could include a component due to the measurement uncertainties. Typically, when you select a sample of stars to analyze, you'll do something like select stars within a given distance limit. As soon as you impose that distance limit, if you have this dispersion here, you're going to introduce Malmquist bias. Because of the dispersion, typically what you'll do is that you'll take the apparent magnitude and you'll set the distance limit. But the absolute magnitude is a scatter in it. So what will happen is that stars that lie beyond that distance limit will scatter into the sample. Stars that lie within the distance limit scatter out of the sample. Because volume goes as density cubed, more stars outside the sample scatter in than stars inside scatter out. So the stars that are outside the sample are actually fainter than you're estimating. You're going to pull them in. You're going to lose some stars that are brighter. It's not a balance. What happens is that the net result is that the average absolute magnitude of the sample is actually going to be fainter than you think it is because of this selection bias. I mean, this plot here perhaps shows what's going on here. Now this is the distance limit that you're putting on the sample. And I guess the other thing to say is that the size of the Malmquist bias is going to depend upon the underlying distribution of the stars themselves. The volume is increasing as d cubed. If you have a density distribution that were to fall off as if you were a density distribution that were to fall off in some way with distance, you would actually get less of an effect in here than you'd expect. So I don't know if that made any sense or not, but the fact is that whenever you are pulling together a set of sample, you need to allow for the fact that there are measuring uncertainties, there are dispersions in the absolute magnitudes, that you're measuring a derived quantity, not an absolute quantity. For Gaia, things should be great, provided the uncertainties in the absolute magnitude for Gaia are going to be so small for anything that I'm interested in that I just don't care about Malmquist bias. If you're going to go beyond the local neighborhood, then bias is still going to be in effect. Lutz-Kelker bias. This is to do with parallax. So when you measure a parallax for a star, the parallax that you measure is going to give you the most accurate absolute magnitude for that star itself. However, there's an uncertainty in measuring that parallax, and that's true even for Gaia. So when you're putting collections of stars together to form a sample, you have to take that uncertainty into account. And this is Tom Lutz. I don't have a picture of Bob Kelker. That's Bob Schomer. Once you're collecting together stars in a sample, you have to allow for this Lutz-Kelker bias. Basically, it's saying that there will be scatter, again, such that the number, depending on the distribution of stars with distance, you're going to scatter in objects where you measure a parallax that's too large, you scatter out objects where you're measuring a parallax that's too small. The true parallax is pi. You measure the observed parallax is either going to be one side or other of that. If there are more stars that have smaller parallaxes in your sample than big parallaxes, you're going to scatter more in, and that has again has a net effect on the mean of the sample. And Lutz and Kelleher came up with this relation here. So this is the uncertainty in the parallax, 5%, 10%, 15%. And this is the correction in the absolute magnitude for the sample in there. So if your accuracy for the sample is 5%, then the correction is only about 0.05 magnitudes. If, as we had to deal with in the past, you're dealing with parallaxes actually accurate to only 20%, you're talking about corrections of 4 or 5/10 of a magnitude in the absolute magnitude of the sample. So these corrections need to be applied when you're using any sample for a statistical measurement. So when you're doing main sequence fitting to globular clusters, you take nearby stars, you take subdwarfs, you have to put in the Lutz-Kelleher bias there because you're using them in a statistical way. Okay, probability plots. This is a handy tool for figuring out whether you've got a Gaussian distribution. The cumulative probability is the probability up to point I in a distribution that that point exists. So for a set of endpoints, it can be generally expressed in this term. You can linearize this distribution by plotting the data against its inverse. And for a normal distribution, the inverse of the inverse distribution is the deviation from the mean expected for the ith point in the standard deviation. Let me just show the example. If you have a Gaussian distribution, it's a fit. This is actually, so you have a set of endpoints here. You fit a Gaussian curve to it. You take each point and you measure its deviation from the mean in terms of this fitted Gaussian. You put them into cumulative distribution. So you're just plotting them from largest deviation on this side to smallest on that side. This curve comes up to be nearly linear. This linear part here, you fit a straight line to it. That tells you the best fit Gaussian to that distribution. This is a very handy tool when it comes to looking at distributions of stellar velocities. I just mentioned that. Star clusters. We're not going to get through this.
Neill, just as a minor comment,
Yep.
if you go back to that tool,
Yep.
that is the most powerful tool that nobody knows,
Yes.
right? I mean, it's incredibly useful for any distribution because it ignores the tail.
Yes.
And if you just compute sigma squared using all your data, you're going to inflate your dispersion.
Right.
But nobody knows about it. I mean, it's remarkably unused.
Yeah, I think the interesting part, I plotted this up here because this is from a paper by Bob Lutz back in the early 1980s. It talks about you can get special graph paper to plot this up.
Graph paper, there's an interesting.
Probability plot graph paper, but I mean this is I didn't necessarily explain it terribly well, but this is a remarkably powerful tool. The other thing is it's good for seeing if you can. You know, we like to do things simplistically. There are some cases where you can see a distribution where there clearly are two components in there. You get two straight lines. That we'll show this later on when it comes to talking about the velocity distribution in the disk. But it really is it's a simple tool to use, and it's very powerful. So maybe I'll talk maybe a little bit about this later on. I think one thing about star clusters, I was going to talk about the convergent point method, and which is something that Guy will use, and exactly how that works. And I guess this main point that whenever you're getting members of a cluster, you go through a series of steps and you're always throwing things out. It's very depressing as you're trying to find a membership of a cluster because they're AND equations, they're not OR statements. Okay, everything gets worse for young embedded clusters. So let me actually, since I'm out of time, just stop there, and I'll come back to this thing later. But let me just end up with the summary slide. And that the Milky Way is an average spiral galaxy. It looks pretty conventional in just about everything. And just as a couple of questions going on, what's the chemical composition of the sun? We'll come back to that. What's the average star formation rate? What does that mean in terms of cluster formation? So I will stop there. Thank you.
Just time for one or two quick questions. Okay, I was wondering, are chemical abundances of the sun, do you think they're likely to settle down to something near the current values, or is it still going to jump around?
There seems to be a clear clash between what helioseismology requires and what is being measured. So that needs to get resolved. I mean, I'll talk a little bit about this later on. And it's actually you have remarkably few lines to measure oxygen in the sun. That's what it comes down to. I don't know. It's clearly, I think it's a big issue that actually needs to get resolved. And it has to be resolved from a helioseismology point of view, because helioseismology really seems to work very well. It works for Kepler stars. And I think that the abundance is probably going to move. But Asplund has to deal with that. So.
Neill, you mentioned the scale height in the disk.
Yep.
And you'll probably come back to this, that it depends on the spectral type of the sample.
No, it doesn't. Well, I mean, yes, it does for early type stars, but for the older stars, it doesn't.
So that you don't see any difference going from G to K to N?
No. I mean, there's no reason why you should, because they're all it's the same age distribution. And I think any difference that have been seen can be explained in terms of biases, because there's absolutely no reason whatsoever that when a particle gets scattered, that what flavor particle that is should make any difference to the galactic potential. So,
And the age distribution.
yeah, I mean the age distribution. If it's the same age distribution, then white dwarfs through to brown dwarfs should all be scattered in the same way.
So given that most of the light you see in a different galaxy will come from the more massive stars, can you compare what you do in the Milky Way to these?
Yes, you can, because remember again, you've lost all of the really bright ones by the time you're getting up to the distances that Van der Kraut and Searle were measuring. So they were measuring G stars, basically. G stars and K giants, actually. So yes, we were measuring the same thing.